Okay, so let's continue our discussion of hidden Markov models. So in the last lecture, we looked at a couple of motivating examples for HMMs. One was based on the casino problem, where we had a fair and a biased coin. And the second example that we looked at was on finding CG islands in a genome sequence. We gave a formal definition of hidden Markov models in the last lecture. And then I briefly mentioned that they are used in a variety of biological applications. So in this lecture, we will continue this discussion and we will look at various problems associated with hidden Markov models. Now to remind you, we are continuing to use the same notations. That is, we will assume that sigma is the alphabet of symbols that are being emitted by the HMM. So in the previous example, for example, the casino problem, that was head and tails. We will denote Q as the set of hidden states. The matrix A will be the state transition matrix, which tells us the probabilities of moving from one state to another, and matrix E is the emission probability. So in this case, this is a Q by sigma matrix in which the KB entry of the matrix tells us the probability of emitting symbol B when we are in state K. So a hidden Markov model, so we will typically denote them as a lambda. So given a HMM model lambda, and it will have 4 parameters sigma, Q, A and E. So we will be using this notation in the subsequent slides. So this was a view of the HMM that we were considering in the last lecture for the casino problem. So you had 2 hidden states corresponding to the use of fair and biased coin, and depending on the state, each state emitted symbol H and T corresponding to the head and tail coin toss. So for example, when you have a fair state, then the symbol H and T are emitted with equal probability, half and half. But when we have a biased coin, then we say that the head is being emitted at probability 3 by 4 and the tail is appearing with probability 1 by 4. And in HMM, because we can transition between one state to other, so from fair to biased and from biased to fair, in this example we can transition with probability 1 by 10. So for this example, the sigma, Q values A and E are shown here. So for this lecture, we are going to focus on 3 fundamental problems associated with hidden Markov models, and we will look at efficient algorithms to solve each of them. The first problem is the decoding problem, in which you are given an observation sequence O and hidden Markov model lambda. The question is to determine the most probable sequence of hidden states. So for example, as we saw in the last lecture, we may know a sequence of head and tails, and we may want to determine at what point the dealer used a biased coin and at what point the dealer used a fair coin. The second problem that we are going to look at is the likelihood problem. That is, given an observation sequence capital O and a HMM lambda, we would like to determine the likelihood of this observation sequence O. The third problem is the learning problem for parameter estimation. That is, here we are given an observation sequence O and we only know the set of hidden states in the HMM. We would like to learn the parameters corresponding to the state transition probabilities and the emission probability. So this is equivalent to training the HMM model given some training examples as input. So, let us start with the first problem, that was a decoding problem, and again to rephrase, given observation sequence O and the hidden Markov model, we want to know the most probable sequence of hidden states. So, the motivation is that suppose you have, for this casino problem, you may be knowing a particular observation sequence. So, in this case that is H H T T T H, and we may wonder, okay, at what point the dealer had used a biased coin and at what point they used a fair coin. Observe that there are multiple possible paths of hidden states. So, for example, the dealer may have started with fair, then moved to biased, and then maybe they used fair coin again. All of these possibilities can generate this observation sequence with different values. So, this observation sequence can be generated by different hidden sequence of different hidden states with different probabilities, and the goal is to find the most probable sequence of hidden states. So, mathematically we can say that we are interested in finding a sequence of hidden states or a path of hidden states pi that maximizes probability of observation sequence O and that path pi. So, we have to maximize this over all choices of paths possible in the hidden Markov model. So, let us see, recall, so how would we solve this problem maybe in a naive manner? Well, the naive manner may be the brute force approach. So, remember that in the last lecture we have seen that if you are told a specific path pi, so if I give you a specific path of hidden states pi and I also give you observation sequence O, then computing probability of O and pi is easy. This is because all we need to do is just need to look at the initial probability, then the state transition probabilities and the emission probability. That is, we just need to walk this observation sequence and this hidden path of hidden states on the HMM and calculate the probability in a very simple manner. So, for example, if you are given pi as, let us say, the length of observation sequence is n, and therefore, you are given a path of hidden states pi 1, pi 2 up to pi n, and let us say our observation sequence is O1, O2 up to On. Now, to calculate probability of O comma pi, all we need to do is to just look at the state transition probabilities, emission probabilities and the initial probability. So, what is the initial probability to start at pi 1, and then for each observation what is the probability of observing OI from state pi I and multiplied by the probabilities of state transitions, that is moving from state pi 1 to pi 2, then pi 2 to pi 3 and so on. So, multiplying all these probability values directly gives us the probability O comma pi for a given path pi and a given observation sequence O. However, in the decoding problem, remember that we have to look for the most probable path. So, we can apply, for example, a brute force approach where we can say, okay, we will enumerate every possible path in the hidden Markov model. We will compute probability O comma pi for each one and we will keep track of the most probable path. So, for example, in the casino problem we could say that, okay, we will consider each and every possible path. So, that would be starting from, let us say, F fair. So, starting with maybe all states were fair, then biased, some biased, some fair and so on. So, we would have to enumerate all possible states and see which of them is most probable for this given observation sequence, and that would tell us maybe that at what point maybe the dealer used a biased coin and at what point the dealer used a fair coin. So, the brute force approach would work well. So, it would give us the exact answer that we need. However, there is one obvious problem here, that is there are n raised to power q different possible paths of hidden states. So, here n is the length of the observation sequence and q is the total number of states, and this can be very big number in practice, which makes the brute force approach impractical. So, how do we solve this problem efficiently? Well, if you look carefully, it turns out that this problem can be split into sub problems, and if we can solve those sub problems efficiently, then we can solve the overall problem as well. And this is the idea used in the popular algorithm, which is known as Viterbi algorithm. So, this algorithm was designed by Andrew Viterbi, which uses the idea of dynamic programming, where we will split this main problem into sub problems, and those sub problems will be easier to solve recursively, such that when we solve these sub problems, we will be able to solve the overall problem efficiently. So, what should that sub problem be? That is the key question when we are looking for an efficient dynamic programming solution. So, let us consider this as a sub problem, where let us call alpha k I as the most probable path for the first I observations. So, we are not looking at the entire observation sequence, we are only looking at the prefix of the observation sequence starting from O1 up to OI. And let us say alpha ki is the most probable path for this observation sequence that ends at state k. So, this is the most probable path that accounts for this observation sequence that ends at state k. Let Ski be the associated probability of path alpha ki. Now, observe that if we suppose look at a longer path for the first I plus 1 observations. So, let us say that let us consider alpha L I plus 1 for the first I plus 1 observations that ends at state L. Let us say that we want to solve for alpha L I plus 1. Now, observe that alpha L I plus 1 must extend one of the alpha 1 I, alpha 2 I up to alpha q I, because the optimal path for the first I plus 1 observations must use the optimal path for the first I observations as well, and that must end in some unknown state from set q. So, given this observation, and how do we decide that which of these should we pick? Well, this we can calculate from the probability values. So, for example, if I want to extend alpha 1 I, the path alpha 1 I to state L, then the probability would be S 1 I times the probability to transition from state I to state L, that is probability of transitioning from state I to state L, sorry, state 1 to state L. So, we can consider individual probabilities for all these paths and find out the optimal path for alpha L I plus 1. So, mathematically we can write this as following. So, the probability associated with S alpha L I plus 1, that is S L I plus 1, should be maximum of Ski multiplied by the transition probability over all values of k from set Q. That is, we can consider all possible states and we can consider the previous calculated probabilities and the transition probabilities, their product, and see which one of these gives us the maximum value. You can easily argue by contradiction that if alpha L I plus 1 does not extend one of these paths, then it cannot be optimal. So, therefore, it must extend one of these paths, and based on that we get the following recursion. We are also multiplying this with the probability factor because this symbol OI plus 1 must be emitted from state L. So, that considers the probability factor for emission of OI plus 1 from state L, and this gives us a dynamic programming recursion. Observe that we can solve these values in increasing order of I. So, for example, I can start by solving S1, so all these SK1 values for all states, then SK2 values for all states, and so on. So, this will be computing first column, computing second column, computing third column, and so on. Another way to look at this algorithm is using the following graph view, where you are solving a dynamic programming table in which the number of rows are equal to the number of hidden states. The number of columns is the length of the observation sequence that is considered so far. So, for example, if we have considered the observation sequence that is up to first 3 observations, then we would be solving the third column of this matrix, and then we will progressively solve fourth column, fifth column, and so on using the recursion that we just saw. Based on this table, we would end up solving for the entire observation sequence, and ultimately we will look at the maximum value in the last column, and based on the trace back we can figure out the optimal path for the given observation sequence. So, this dynamic programming is very similar to the other dynamic programming algorithms that we have seen in the earlier lectures of this course, and also the trace back also works in a similar manner, that is, we keep going back to see what value led to that optimal value, and based on that choice we keep moving backward and until we find the optimal path that led to the maximum probability value. So, some other details of this algorithm, well, first is initialization, because the dynamic programming algorithm has to start with initializing the probabilities, and that we can do easily for the first column. So, observe that for the first column initializing the value is very easy, that is, you look at the initial probability, that is, what is the initial probability of state k, that is, what is the probability of pi 1 to be k, multiplied by the probability of emitting the first observation symbol O1 from state k. Also, once we have the final answer, that is, suppose pi star is the optimal path, then the probability of O comma pi star is given by the maximum value in the last column, that is, maximum value over all skn, where k comes from the set Q. And once we have figured out the maximum value, as I said, the actual state sequence can be found by backtracking. So, what would be the running time of this algorithm? Well, observe that the size of this dynamic programming table is n times q, where n is the length of your observation sequence and q is the set of hidden states. So, and for each element of this dynamic programming table, we are looking at all the states to compute that value. So, we are looking at the entire column of the dynamic programming table in our recursion. So, therefore, we are spending order q time for each element. Therefore, if you consider these two factors, the time complexity of this algorithm becomes n times q square. And observe that that is a much significant improvement over the brute force algorithm, where we were enumerating over all possible paths that were exponentially many. So, this polynomial time algorithm is significantly more efficient, and that this was a major update for HMMs that led to the practical applications of HMMs for various domains. So, moving ahead, one other detail of this algorithm is that we often want to calculate these probability values using logs. So, for example, if you see, the recursion involves the multiplication of probability values, and as we keep going forward from column 1 to column 2, column 2 to column 3, we will end up achieving very small values. So, for example, if your probability value is 0.1, then you multiply it by 0.1, 0.1 and so on, you can see that this value becomes very small as you keep moving forward. And when you have very small values, that can lead to underflow errors on computers. And to avoid these very small values, what we can do is we can compute this recursion using logs, because remember that in log, when you are taking the product of a log, then the product becomes equal to summation. And because of this property, because when we are taking logs, we can keep the values larger, and that helps us prevent numerical errors. So, when we convert this recursion into log space, then we can take log on both sides. So, that would become that log of this value will basically become max of log, summation of log of these values plus log of the final value. So, all these, so the product in the previous recursion can become now summation of these values. So, that was a practical implementation aspect, that normally when we implement Viterbi algorithm, we have to take log of the probability values to avoid numerical errors. So, let us also look at one toy example to understand the Viterbi algorithm better. So, this is a toy HMM where you have two hidden states H and L. So, this is a model, HMM model, that for modeling DNA sequences, in which H stands for high GC content and L stands for low GC content. And depending on the region of the genome, we have different emission probabilities. So, at the H state, we have these emission probabilities, and at the L state, we have different emission probabilities for A, C, G and T symbols. So, given this HMM, let us say that the question is to identify the most probable state path for the following DNA sequence GGCAC TGAA. So, for this DNA sequence, what is the most probable state path for this HMM? Now, we can again think of the brute force algorithm. So, if we think of the brute force algorithm, now remember that this sequence length is 9 in this case. So, the brute force algorithm will need to consider 2 raised to power 9 possible state paths, and for each one we will have to calculate the probability of PR O comma lambda. So, for each one we will have to calculate the probability and then identify the most probable state path. and clearly this is a very big value. So, we will not be doing that. The better way is to run the Viterbi algorithm. So, in the Viterbi algorithm we are going to use the log of the probabilities to make it more convenient while calculations. So, let us start with the first symbol, that is the first symbol G of the sequence. What is the probability in log space that G at the first position was emitted by state H? Well, as we saw from the initialization component, that for this we have to consider the initial probability -1. So, remember that all these probability values have been converted into log space as well. So, half, for example, log half is equal to -1, and that is why we are using all these logarithmic values. So, the initialization probability will depend on the initial probability of state H multiplied, or in this case added with the emission probability for emitting symbol G. So, if you add -1 and -1.7, you get -2.7 as the log probability value. Similarly, we can ask the same question, that what is the G probability that G at the first position of the sequence was emitted by state L of the HMM, and again we would do a summation of -1, that is the initial probability, and the log of emission probability, that is -2.3. So, again in this case we end up with the probability log probability value -3.3. So, as we saw in the Viterbi algorithm, we will move one column at a time. So, now we will consider the observation sequence. So, that is the first two characters of the observation sequence GG. So, now we can ask what is the probability that the symbol G at the second position of the sequence was emitted by state H. Well, in this case again we will look at the log emission probability plus, now we have to decide whether we want to extend the whether we want to extend this path from state H or whether we want to extend the path from state L. So, for that we will take the maximum of both probability values. So, that will be maximum of PRH plus transition probability of H to H, that is we say that the previous sequence ended at H and now we are transitioning to from H to H, or we extend the path from state L and then go to H. So, both probabilities we are considering. So, this PRH G1 plus moving from H to H, comma PRL G1 plus moving from state L to H, and once we do this calculation we will end up with the value -5.4. This you can verify yourself. Similarly, we can again ask what is the probability that G at the second position of the sequence was emitted by state L, and again we can apply the same recursion as we saw just now. So, if we continue this procedure, we can fill the entire dynamic programming table and we will have to look for the better value, that is maximum value in the last column, and then we would trace back from the last column to identify the most probable path of hidden states. So, I encourage you to solve this problem yourself completely, and what you would end up with is the most probable path would be HHH LLLLL. That is, it is telling you that the DNA sequence that we are considering has a high GC content at the start and it has low GC content towards the end. So, that is the prediction that you are getting from this HMM. So, this covers the decoding problem where we solved the decoding problem efficiently using Viterbi algorithm. Let us also briefly look at the other two problems, which is the likelihood problem as well as learning problem. So, likelihood problem basically now you are given an observation sequence O and we are directly asking the probability of that sequence O for the given HMM. So, this is equivalent to saying that probability of O will basically be probability of O comma pi over all possible paths of hidden states pi. And again one can think of a brute force way to calculate this by enumerating all possible paths of hidden states. And again, as we saw earlier, the brute force way is going to be slow. So, again we can think of an efficient way of calculating, and as you can realize, this again falls into the class of dynamic programming problem, where we can apply the same principle that we saw for Viterbi algorithm. We can use the same principle here as well and design a dynamic programming algorithm for this problem as well. So, again the same applying the same principles, let Fki be the probability of getting the first I observations using a path in which the last state is k, and based on this we can calculate Fli plus 1 as the probability of Oi plus 1 emitted from state L multiplied by summation of Fki times the transition probability from state k to state L, and this is over all states in Q. Now, observe that the key difference between the Viterbi algorithm and this forward algorithm is that the max sign that we were using before, this becomes a summation sign in the forward algorithm, because we are considering the adding up the probabilities over all possible paths in the HMM, and it behaves similarly. So, the runtime is equal to what we saw for the Viterbi algorithm, and again you can see that this is a very efficient algorithm compared to the brute force mechanism. So, ultimately we have to basically compute this recursion in the same way, and the final answer would be the sum of the values in the last column. Now, for the third problem, that is the learning problem, here we are given an observation sequence O, and but we do not know the parameters A and E. So, this is a much harder problem because now we do not have the hidden Markov model fully specified to us, and in practice compared to the Viterbi and forward algorithms, this is a much harder problem because typically estimating the parameters of the model is more difficult. So, here the strategy, the principle is basically that let us say that the theta is the vector representing the unknown HMM parameters A and E, and let us say that the probability of observation sequence O given parameters theta, let us define it as the likelihood of sequence O given some assignment of parameters theta. The learning objective is to find the maximum value of this probability over all possible theta values. That is, what assignment can I do to the parameters so that the probability of this observation sequence is maximized. In practice, we will typically work with not just one observation sequence, we will have many examples for training. So, let us say our training set includes m strings of observation symbols, and in that case our objective will be to maximize the probability of all these observations over all possible space of parameters. And as you can see, this is a difficult optimization problem because we are optimizing this quantity in a multi-dimensional space theta. And as it turns out, there is no tractable algorithm for solving this problem exactly. So, typically therefore, we use heuristics that would iteratively improve this quantity, and we will iteratively try to improve our estimation of the parameters. So, for example, a popular algorithm is the Baum-Welch algorithm that we are not covering in this syllabus. So, that covers the overview of all these three problems that I wanted to convey, that the decoding problem, the likelihood problem and the learning problem. And as a result of efficient algorithms for all these problems, this is why the hidden Markov models are used for a large variety of problems, both for computational biology as well as many problems outside computational biology as well. Thank you.